Hi, everyone. Thanks for coming today to my talk. So I'll be talking about the new CEH-Gridded estimates of areal rainfall for CEH-Gridded dataset. And this is the outline of my presentation. I'll first start with an introduction to talk about the background and the motivation. Then I'll briefly talk about the underlying rain gauge data. Then I'll explain the methodology. After that, I'll show a few results on analysis that's been done on the data set. And then I'll present some subproducts of the data set. And following that, I will show a few examples, actual examples of use. Then I'll explain how to access the data, and I'll finish off with some ideas for future work. So starting with the introduction. So what was the background? What was already there when we first started the project? So there was already another rainfall gridded data set here at CEH, which has been developed under SURF project, Continuous Estimation of River Flow project. But that was only a part of a bigger project, and there was only limited time assigned to it. And so the priority was given to try to minimize the coding and computing time. So that means they somehow had to compromise on the quality. So just before I continue, I want to make sure everybody understands what I'm talking about when I say gridded data set. So we have, as input, we have a network of rain gauges, which are point time series of data, either daily or monthly. Then for every time step, either day or month, we apply some sort of spatial interpolation method to then get us as an output spatial data, the data being interpolated between rain gauges. And if we zoom into an area, then you can see the spatial resolution. And for this talk, whenever I'm talking about gridded dataset, I'm talking about 1 kilometer resolution. So now that I've made that clear, I can continue with. So there were some known problems with the SURF rainfall dataset. First, the interpolation method itself was not the best one. It was a method called the triangular plane method. It has the advantage that it's very relatively simple to code and quick to compute, but it only uses the 3 closest rain gauges, even though if you have many more around. So it doesn't optimize the use of the available data. Another problem is that we also, to try to minimize the computing time and to simplify the algorithm, they've decided not to use rain gauges that had many missing data. So if, for example, a rain gauge had 3 months of data out of a year, they just wouldn't use that rain gauge at all, even though those 3 months were good data. Another problem is, so the SURF rainfall grids were daily grids, but CEH also had another set of rainfall grids which were monthly grids, and the two data sets weren't using the same interpolation methods, and so the two data sets were not consistent. And also because it was within a project, it was a one thing. The data set was originally developed for 1961 to 2000. It's been updated after that, but not on a regular basis. It was just when there were lots of demand for it. And last thing is that CEH, we've recently updated the data set of rain gauge hold at CEH. It's now in line with the Met Office database, which was not the case when SURF rainfall grids were developed. So, what was the motivation to create a new rainfall data set? So we've seen that SURF rainfall grids were not perfect, but even like that, they were very popular and widely used. It's been used by many people. So we really felt that there was a need within the hydrological community for fine resolution rainfall grids. And also we've identified a demand for long-term time series that goes back into historical data. So that's from the user point of view, but from the data management point of view, we've realized that we needed to have a strategy for long-term stewardship and also explicit data licensing term and condition to avoid misuse. So the objectives for the new gridded dataset is to make a better use of available data, to have monthly and daily grids consistent, to use a better interpolation method, and we also wanted the dataset to be compliant with British standards. And all these objectives led to the birth of CEH-Gridded dataset. And just a reminder of what CEH-Gridded stands for. It stands for Gridded Estimates of Areal Rainfall. And the little picture here is to help you remember the name, because with so many acronyms we have, yet another one. Hopefully it helps, the visual help is useful. And so what is CEH-Gridded dataset? The main product is the 1 kilometer gridded rainfall daily and monthly totals for the UK, going from 1890 to 2012. And we're planning to update the dataset yearly. And there are some subproducts, the main one being daily and monthly grids of the distance to the closest gauge. And there are also some ancillary grids which give information on missing data, but I'll talk about this a bit later. The main features of CEH-Gridded is it's been developed with the hydrological community in mind, so that means the spatial and temporal resolution are ideal for studying hydrological processes. It has a long record, it goes back to 1890. It's free to download, not only for CEH staff, but also if you have partners outside CEH, it's free for them as well, even for commercial use. The only restriction we have at the moment is you're not allowed to sell the data. We're giving it out for free, so that seems fair enough. And when you're not allowed to sell products that are heavily based on the dataset. And it's based on observed data, which are in line with Met Office database. So I'm going to briefly talk about the underlying rain gauge data. So these are the main bodies that collect rainfall data in the UK. They are not the only ones, but they are the main ones. And so all the data is then collated and quality controlled by the Met Office. And once per year, it's sent to CEH. And here it's managed by the National Rainfall Archive. And we hold monthly and daily data. So this slide is something important to keep in mind, that the rain gauge network density has varied in time. This is going to be important because it's going to affect the quality of the data set depending on when and where you're interested in. So before 1961, there were very few stations digitized. Then in 61, most rain gauges were digitized with a peak in 1975. And since then, it has decreased, and we have currently around 2,700 gauges. And this is the same information, but shown spatially, so that you can see how the density has varied. Just want to point out here that if you look at the 1910 map, although there are some areas such as Scotland or Wales that are quite poorly dense, but there are some other regions such as West Midlands or the London area, which are actually not that bad. So the quality will really depend on where you're interested in. Now I'm going to explain the methodology. So the interpolation method that was used for this dataset is the natural neighbor method, which is one of the recommended methods by the British Standard Institution for gridded rainfall estimates. And the natural neighbor method is based on Thiessen polygons. So if you have a network of points, Thiessen polygon for a given point is the area surrounding that point, within which every single point is closer to that point than to any other point of the network. So the natural neighbor uses those Thiessen polygons, and if you want to calculate the rainfall at a point, you draw a new Thiessen polygon for that point, and the rainfall is then calculated as the weighted average of the rainfall measured at the surrounding rain gauges, and the weight that is applied is, for example, for that red circle point, it would be the area that has been removed from the original polygon divided by the area of the newly introduced polygon. And we've also applied normalization by SAR, which is the standard period average annual rainfall, to take into account the long-term pattern, the spatial pattern of rainfall. And just something I wanted to say here, within for the CEH-Gridded dataset, the network of polygons were calculated for every single day. So if, for example, on gauge number 1, if there was a missing data tomorrow, then we would just recalculate the whole network of polygons. And for the normalization by SAR, we've used for Northern Ireland the Metarian SAR, and for Great Britain the Met Office SAR. And lastly, we've also applied a monthly correction factor to make sure that the daily and the monthly grids were consistent. So for CEH-Gridded, the sum of the daily rainfall totals for 1 month are equal to the monthly rainfall total for that same month. So now I'm going to show you a few results of some analysis that's been done on the dataset. So for validation purposes, we've chosen 14 sites, 7 in Scotland and 7 in England and Wales. And we've studied over a period of 4 years using daily data. So what we've done is we've removed those rain gauges from the network, and we've calculated the grids without using those gauges, and we've used them for validation. And those sites were chosen in areas with high spatial variability in rainfall. The reason for that is because that's the regions that are likely to be more problematic for the interpolation method. So we really wanted to test the method where it's likely to perform worse. So this is the results. On the y-axis, you can see the error. On the x-axis, you can see different ranges of observed rainfall, with low rainfall on the left and high rainfall on the right. England and Wales is in blue, the blue boxes, and the red boxes are Scotland. So what we can see here is the error is small when there's no little rainfall, although we do have some outliers in Scotland, and the errors are larger for the bigger rainfall events. And overall, we tend to slightly underestimate the biggest rainfall events. And I just want to say here that even though the range of error, especially for the higher rainfall events, the range looks quite big, but if you look at relative errors, actually it's almost always within 5% error, so it's not as big as it looks here. So we also wanted to see whether the CEH-Gridded rainfall were really better than the old surf rainfall grids. So for that, we've used 138 CEPA tipping bucket rain gauges, which are independent source of data. So this is where they are located, and in blue you see the network of rain gauges that we've used to derive the grids. And this is the result, similar graph to before, the error on the y-axis and the different ranges of observed rainfall on the x-axis. The green boxes are surf rainfall, and the brownish ones are CEH-Gridded. And we can see that it does improve. The range of error is much smaller for CEH-Gridded, and the median error is much closer to 0 with the new data set. So that's good news. We also wanted to assess the effect of the network density, and we've used the same CEPA tipping bucket rain gauges for that. And this is the result. So you can see on the y-axis the median absolute error, and on the x-axis the distance to the closest gauge. And the different graphs are different magnitudes of rainfall event, with, again, on the left low rainfall and the right high rainfall. What we can see here is really what you would expect, that the error increases when the distance to the closest gauge increases. And this is even more so for the largest rainfall events. So that leads us to the next section, the subproducts of the data set. So as a consequence of what I've shown on the last slides, that the error increases when the distance to the closest gauge increases, is that we've decided to calculate the minimum distance grids, which are the grid of the distance to the closest gauge. And we provide those minimum distance grids together with the rainfall grids. And we very highly recommend users to use those grids because they will give you the indication of the confidence you can have in the data, especially if you're looking at historical data before 1961, because in some areas, the density of the network is likely to be low. Another consequence of this observation is that we've decided just not to calculate the rainfall above a given threshold. And we've set that threshold to 100 kilometers, which can seem very high still. But the reason why we've done that is because we wanted to ensure full coverage after 1961. The reason for that is because we've been told by modelers, who are one of the main people that are going to use this data, that the data set was useless to them if it had gaps in it. So they'd rather have data with high uncertainty than no data at all. So we wanted to at least to have after 1961 fully covered. So before that, there are some gaps. So this is the map of the missing data. The gray areas are the areas with no missing data for the whole period. The dark blue bits are like less than 10% missing data. The light blue is less than 20%, and it's only in the very north of Scotland and some islands that you get around 30–40% of missing data. And to summarize that information, we also provide some ancillary grids with the information for every single grid cell, first year of missing data, the last year of missing data, and also the total amount of missing data. So now I'm going to show a few examples of use. The first example is the Driver project, which is an international project which tries to link drought indicators with impacts in a drought monitoring and early warning context. And we've used CEH-Gridded in this project to derive some drought indicators, such as the standardized precipitation index. And this is the 2010-2012 drought. Another example is the Joules land surface model, which has a UK version called CHESS, and CEH-Gridded was used as one of the driving data to run CHESS. Third example is the National River Flow Archive here. CEH is planning to derive some catchment rainfall average time series that they will then make available together with the rest of data they hold. So I would be curious to know, what would you use CEH-Gridded dataset for? Apart from the three examples I've given you, I've had requests for the data from a variety of people from different fields, such as hydrological modelers, catchment scientists, people studying floods, both historical and both recent and historical floods, although the data doesn't go back far enough so that you could study this particular event. It still goes back to the beginning of last century. People studying droughts, land surface modelers, colleagues at BGS studying groundwater, statistician doing some time series analysis, and some ecologists doing some freshwater, working on freshwater ecosystems. Now I'm going to explain how you can access the data. So the data is stored in NetCDF format, which is, I think, currently the most common way of storing and sharing multidimensional spatial data, scientific data, because it's highly portable, it has built-in metadata, etc. And the data is hosted by a thread server, which is at the moment still a prototype, which is only accessible from within CEH. I'm not going to talk too much about this because we already had a gridded dataset workshop sometime back in spring, but I'm just going to say a few words about it. The threads data server will hopefully be publicly available sometime soon, in November, before winter, hopefully. The guys in Lancaster are working hard on it, setting up user authentication and other technical stuff that sound very complicated to me. But yeah, so we're getting there, and it will be soon available. And once it will be publicly available, then you'll be able to directly access the data through the gateway. The entry for the dataset already exists, but when you try to click on the actual link that should bring you to threads, you get a message saying that the data is under embargo. But this will be solved whenever the threads becomes publicly available. And we're also quite pleased to see that when you Google CEH-Gridded, it's the first result that you get. And so the Threads data server has a range of functionalities that are useful to users, such as you can visualize the data, you can download it, although I wouldn't recommend to do that unless you're only interested in a couple of years, because the data is huge, and there are other ways of accessing the data which are more efficient, I think. The web map and web coverage services allows you to directly access the data through GIS systems such as ArcGIS or QGIS, so you can actually load the data from the server without having to download it. And you can also do some spatial and temporal subset or point extractions. Or what I personally find most useful is you can use OpenDAP to actually access the data directly from your Python or R code or whatever you use to program. I'm not expecting to read this. This is just a code I've written that I'll make it available together with the slides that will be uploaded on the internet. You can use this code as a template. It's a code that shows you how you can access the data in Python without having to download the data. I'm sorry for people who code in other languages. I only have an example in Python, but I know there's equivalent functions in R, for example, or I'm sure in other languages as well. Now, just before I finish, I'd like to talk about a few ideas we have for the future work. First, we have a web portal under development under the Land Water Information System project, which will have a collection of tools. You'll be able to extract catchment average rainfall, to do some spatial and temporal aggregations and things like that. But it's work in progress. It's not ready yet. Something else we are really keen on doing is do some proper uncertainty analysis, because at the moment we just provide the minimum distance grids and we ask the users to make their own decision whether they trust the data or not. Ideally, we would like to be able to quantify the uncertainty and provide an uncertainty grid. But it's not a simple task. It's quite complex, and if we find the resource to do that, it's certainly something we would like to do, and we would then incorporate it in future versions of the dataset. And we also want to write a document with guidance on how to use the data and set some recommendations on minimum distance that you can trust and things like that. And this is a summary slide with the key points I want you to remember from my talk. So CEH-Gridded is a 1 kilometer gridded rainfall daily and monthly totals dataset for the UK, which supersedes the SURF rainfall dataset. It goes back to 1890 and it will be updated yearly. The minimum distance grids give an indication of the confidence you can have in the data. And please do use those grids, especially if you use historical data. And Thread server will be fully operational, hopefully, sometime in the next few months. And just before I finish, I'd like to spend a minute to acknowledge the rest of my colleagues who have contributed to this project, especially Virginie, who is now on maternity leave, but she's the one that has managed and coordinated the whole project. Dave Morris, who is now he's now retired, but he has lent us his brain and his knowledge to make sense of all of this. Ilaria is the statistician that did all the crazy analysis. Harry is that guy that with his experience and expertise always came up with the good ideas and solutions to every single problem we would bump into. And I'm the one that have actually developed the code to derive the grids, to produce the grids. And Jules, Olivia, and Steve have helped us with data preparation, production, and validation. And the projects that have funded this work are Matt and David's projects. So thanks to all of them. And there's also a whole bunch of other people who have contributed to different extent in different ways, and many of them work behind the scenes. So we wanted, on behalf of the project team, I wanted to thank all. And that's it. Thank you very much.